Hi everyone, my name is Derek Vigar and I'm a professor with George Brown College here in downtown Toronto, Canada. I lead the project management specialization here in the School of Business, and I wanted to take a few minutes to help explain an extremely important concept in project management, and that is the ability to calculate a project critical path. Now, many of you have likely been in a meeting or at an office and heard the expression, we have to keep things on critical path. It's a very popular expression in business, but what does it actually mean? Well, funny enough, more often than not, people use the expression without really understanding what it's all about. My goal in putting this little video together is to clear up some things around critical paths and walk you through one of the techniques so that you yourself are actually able to properly calculate a project critical path. It's quite a valuable skill because being able to do this gives you tremendously valuable information and insights. It will help you prioritize activities, assess the impact of delays, and ultimately determine your project timeline and schedule. So lots of good stuff. But before we get there, let's just give ourselves a bit of a refresher on critical paths. So what is a project critical path? Well, very simply put, it is the longest path of connected activities from start to finish in a project. If I can sit down and map out the longest path for my project, in essence, what I found is the estimated timeline or duration for how long the project will take. So if the client or my boss is putting an estimate or a proposal together and they want to know how long a project is going to take, I can calculate the critical path in order to give them an answer. So to illustrate this, as a very simple example, say I'm the project manager for a project involving only 3 tasks. Now, I'm just going to use letters to characterize these tasks, as they really could be anything. But just to be clear, these are the tasks generated by the work breakdown structure, or WBS, and these all need to be completed in order for me to finish my project. So task A, which again, it could represent anything. It could be a marketing task, hiring people, building, whatever. Task A will take 5 days. Task B will take 7 days, and task C will take 4 days. Now, before I show you a visual, I want you to take a second and think about how long this project will take. Again, you have 3 tasks, they're all starting at the same time. When will you be done this project? Okay, let me present the visual of a Gantt chart to see if it helps in answering this question. As you can see, task A, B, and C are all starting on the same day, which I've labeled day 0. The project is over when all the tasks have been completed, and that doesn't happen until day 7 when the longest task, which is task B, wraps up. This means that task B is our critical path. It's critical because any change to it will impact our project timeline. To see this, say we figured out a way to finish task B sooner by a day. What would happen? Well, all the tasks will be wrapped up by day 6. Instead of day 7. So in fact, we've reduced our timeline by 1 day. On the other hand, let's say there was a delay for some reason to task B, and it ends up taking 8 days. Now 8 becomes the new finish date for the project. So as you can see, task B is quote-unquote critical. You can see how task A or task C doesn't have this special critical characteristic. This is important to be able to identify because so often when a project starts to slip and there's pressure to speed things up, a typical response may be to push everyone to work harder or faster. Well, as you can see, if we push the person working on task A to go faster, say we pay them to work overtime or on the weekends to go faster and they finish in 3 days instead of 5 days, it's really not going to make that much of a difference because we still have to wait for task B to be completed before the project is totally done. So we've incurred that extra cost of paying overtime, but we haven't ended up speeding up the timeline. One other thing you'll note is that I use the term longest path in the definition of critical path. I did this because sometimes there are relationships or dependencies between tasks. A common one would be a situation where a task cannot start until another task has been completed. So an application of this might be that I cannot complete the task of printing a concert poster until previous tasks of confirming the band or confirming the date and the location, they've been completed. So those have to be completed before I can print that poster. Any project that requires a project manager will likely have a number of these dependencies, and it's your job to map them out and make the connections because it influences the critical path. So let's say, for example, that task C cannot start until task A has been completed. In essence, we've joined these tasks to form a path of activity. This newly formed path is longer than task B, so by definition, it's now the longest path. Therefore, AC becomes our new critical path, and we expect the project is going to take 9 days to complete. So now that we've covered our basis, let's walk through an example that's a bit more involved. Essentially, to be able to calculate a critical path, we need 3 pieces of information. First, a list of tasks, and here we have a project that has 6 tasks labeled A through F. Next, we need to know how much time is expected to be necessary in order to complete each of these tasks. That's the second column. In this example, task A will take 5 days, task B will take 4 days, and so on and so on. And finally, we need to know the dependencies, or what we call precedence, between the tasks. These are the relationships between the tasks that we just talked about. In this example, task A and task B, they can start right away. There is nothing that has to be completed before they can start. You can see from this list that task C cannot start until task A is complete. Task D and task E depend on task B being completed before they can begin. And finally, task F cannot start until both tasks C and D are finished. Now that may sound like a mouthful, but we can use critical path and the inputs from this list to derive some really important management information about our project. Number 1, we can figure out how long this project is going to take to complete. A question I'm sure the client and my boss, they're very eager to know. And we'll do this by calculating the critical path. Number 2, we can figure out which individual tasks are critical, and this is important because it prioritizes for us which tasks we need to keep a close eye on and closely monitor. Knowing where to focus is going to be important when we get into bigger projects with hundreds or even thousands of tasks. And number 3, the other side is that we can identify those tasks that are non-critical, and this is valuable because it will allow us to figure out how much slippage, otherwise called slack time, buffer, cushion, wiggle room, or contingency, we have with those tasks, and we'll know exactly how much they can be delayed before it becomes problematic. So, how do we map the critical path and answer these juicy questions? Well, we construct a network that's called a critical path diagram, specifically an activity on arrow critical path diagram. And let me show you how. Basically, this diagram is going to look like a map, and I'm going to draw it using 2 symbols. I'll draw a circle every time that there's a project event, so the start or stop of something significant, and an arrow for each of the tasks. To start, by definition, every project has a start and an end date. These are pretty significant events, so I'm going to draw a circle to represent those points where the project starts and stops. I then want to scan through my list to identify those tasks that can start right away, right from the project start. Can you help me out? Look at the table and tell me which tasks can start right away. Well, if you said task A and task B, you're correct. They have no preceding activities that need to be completed before they can start, which means they can start right away. So let's draw task A, which takes 5 days to complete. The event to which task A starts is the project start, so we already had a circle there. And we're going to put another circle on the end to signify where task A ends. The arrow represents task A and its 5-day duration. Let's get task B up there. Again, it comes from the start because there are no preceding activities, and we put a circle for the event that signifies where task B stops. And the arrow represents the 4-day duration to complete task B. So those are the 2 tasks that can start right away from the project start, and we're well on our way. So now that we've drawn the events where task A and task B stop, we can look to our list again in the top left-hand corner and identify the next series of tasks. And those are the ones that depend on task A or task B completing before they can start. So now that we've finished A and B, can you identify which tasks are now ready to start? At this stage, we're ready for task C, task D, and task E to start. C takes 6 days from the point where A stops. D takes 2 days from the point where B stops. And you can see that E also starts from the same point where B stops, and that's going to take 5 days. Now we have a lonely task F left, and this one's a bit interesting because it starts from the single event where C and D stop. But if you look at the map we've drawn so far, you see that there are 2 separate events, one for where C stops and another for where D stops. So how do we draw F? Well, the key is that we need one event to signify the stop of C and D. So let's just erase what we've previously drawn for D, and instead draw it so that it feeds into the same stop event as task C. So it's going to look like this. All of our rules are still maintained. You can see D still starts once B stops, but now we have a single shared event for which we can start F. So as you can see, we now have F starting. It takes 8 days and then it stops. It starts at the point where C and D finish. And there we go. We've gotten all our tasks up on the map. Now this is a network diagram, which means it has to be closed. So we take our loose branches for task F and task E, and we want to bring these into the event for the project end. Okay? Effectively what this is doing is it's closing our network. And there you have it. Voila! This beautiful work of art is a critical path diagram for our project and is going to provide us with insights to those 3 key questions we stated off of the top. So let's go through them again. Number 1, how long will the project take to complete? Well, to answer that question, we're going to have to calculate the critical path. And by now, you're probably jumping out of your chair to tell me that means we have to find the longest path from start to finish. So let's pull up our diagram and look at it as a map. What are all the various ways or routes or paths that we can take to move forward from project start to project end? Well, to start, one of the paths that we can take is ACF. ACF runs along the top of the diagram. Let me highlight it here. And the total duration to complete ACF is 5 days. 5 days for A, plus 6 days for C, plus 8 days for F. And that equals a total of 19 days. So the path ACF in total is going to take 19 days. Can you see the other 2 paths? Well, we can also go BDF. Let me highlight it through the middle here for you. And that's going to take 4 days for B, plus 2 days for D, plus 8 days for F, for a total of 14 days. So our second path, BDF, takes 14 days. And that leaves one final path. It's BE. Okay, BE runs along the bottom of the map. And it's going to take 4 days for B and 5 days for E, for a total of 9 days for BE. So we have 3 paths. And if the definition of critical path tells us that we have to look for the longest one, that means our first path, ACF, is our critical path. And we expect the total duration of our project to be 19 days. Which is cool because remember, all we had at the beginning was a list of data points and inputs. And from that, we were able to construct a critical path and make an educated estimate as to how long this project will take. So in this process, we've also answered our second question and identified those tasks that are critical and must be closely monitored. A, C, and F will be dictating the timeline of 19 days. So if I was managing this project, you could bet that I'd be closely watching and supporting those tasks to ensure that they stay on track, because we know that any delay to them will extend the timeline of the project. So this leads us into our final question, which is to figure out something we call the slack time for all those tasks that are non-critical, or in other words, not on the critical path. We want to identify those non-critical tasks and calculate how much they can slip or slack before the timeline is impacted. So let's pull up the work that we did in calculating our critical path. In the previous question, we determined that the critical path of the project was 19 days. Okay, so this means that A, C, and F are our critical activities. If A, C, and F are critical, by default that leaves B, D, and E as our non-critical tasks. So what's the big deal? Why is it important to identify a non-critical task? By name alone, it doesn't sound very important, so why should we care? Well, we care because eventually, if there is a long enough delay to a non-critical task, it might actually become a new longest path, and therefore could take over and become our new critical path. To illustrate, let's look at task B as an example. If you are managing this project and the person responsible for task B comes to you and tells you that they need more time, how much could you give them and still be able to deliver the project in 19 days? In other words, how many days can task B slack before it impacts the project timeline? Well, to answer that question, we first have to identify all the paths that involve task B. So you can see that B is a part of both path BDF and of path BE. Now, a quick approach is to simply subtract the critical path from each of these paths that include task B. So, for BDF of 14 days, we subtract the critical path of 19 days, which gives us 5 days of contingency or cushion or wiggle room before we go over the critical path. For BE of 9 days, when we subtract the critical path of 19 days, we are left with a contingency or cushion or wiggle room of 10 days before we go over the critical path of 19 days. So we've effectively identified 2 different levels of slack. In one path, we have 5 days of room, and the other path is telling us that we have 10 days of room. There's only one person doing task B, so which is the right answer? Can task B be delayed by 5 days or 10 days? The answer is 5 days. Okay, why? Well, think about it. 5 is the only answer that doesn't push a path over the critical 19-day marker. If we add 5 days to BDF, we land on 19 days, so 14 plus 5, which is okay. If we add 5 days to BE, we land on 14 days, so 9 plus 5, which is also okay because it's not over the 19 days. But you can see this doesn't hold true for 10. If we add 10 to BDF, we get 24 days, 14 plus 10, which effectively would make it the new longest path, which would mean it's the new critical path, and our timeline would extend from 19 to 24 days, which would be bad. You can see that adding 10 to the shorter path of BE would keep it at 19 days. However, it causes BDF to go over 19 days. So to offer some advice, the quick and simple rule is that when you have a non-critical task like B appearing in multiple paths, once you subtract the critical path, the slack time is always the lowest number. And this is true because the lowest number will always work in keeping all the paths from going over the critical path. Having fun yet? Well, let's make sure with one final question. Let's use that same example and answer the question for another activity. How many days can task F slack before it impacts the project timeline? So here are the 3 paths we figured out, as well as the critical and non-critical tasks we identified. Before we get into it, do you want to take a crack at it? Press pause and figure out the slack time of F. Well, there's a simple and straightforward way to answer this, but let me take you along the same approach that we learned for the last question. We highlight all those paths that include task F. So that's going to be ACF and BDF. We then subtract the critical path from each. So for ACF, we subtract 19 days. And we subtract 19 from 19, that's going to equal 0 slack. For BDF, we subtract the critical path of 19 days from BDF's 14 days, and that's going to equal 5 days of slack. And just as in the last example, we have 2 choices. So which is it? Is the slack of F 0 or 5 days? Well, according to our rule, when calculating slack in multiple paths, we always pick the smallest number because it works in all the paths. So the answer would be 0. And that brings us to a key rule, okay? And that is all tasks on the critical path have a slack time of 0. If you think about this for a second, it makes sense. The critical path is already the longest path and the baseline for your project timeline. If something on the critical path was to be delayed, it would have to extend the timeline. So there's no contingency or cushion or wiggle room. As soon as you recognize that a task is on the critical path, no matter what other path it's on, it must have a slack time of 0. Well, that should wrap things up for now, and looking back, we definitely went through quite a bit about critical paths. All of it boils down to using 3 different pieces of data to derive 3 different important management insights. If we know the tasks, the times, and the precedence or relationships between the tasks, we can effectively create a critical path diagram. Doing so allows us to figure out some pretty important stuff about our project, mainly how long the project will take to complete, which tasks need to be closely monitored, and how much non-critical tasks can quote-unquote slack or be delayed before they impact the project timeline. Now you'll just have to put this to practice on bigger projects. So I hope you enjoyed this little walkthrough on project critical paths and found it helpful. feel free to contact me at the George Brown School of Business, Arts and Design should you have any feedback or like to further discuss. My email is dvigar@georgebrown.ca and my phone is 416-415-5000, extension 3391. Take care, have fun, and we'll talk to you again soon.